This is the first of what will probably be about 3 videos, perhaps, maybe 4, we'll see how it goes, about sections 5.1 and 5.2, which are really, really fundamental sections as we try to understand nonlinear systems, focusing on what we can understand about them without having to use the computer, though we will certainly use the computer to try to illustrate things. To start things out and whet your appetite, though, for what we're going to do here ultimately, we need to focus on the most important thing, which is what kind of jokes are going to go on. And, well, for these perhaps 3 videos, I've got 3 jokes, and I'm labeling these Dr. Kinney's long and lame jokes. Okay? So this is what you have to look forward to. I really like long, lame jokes. I think it's lots of fun to just sort of wonder how they're going to come out lame. That's probably the main reason. Anyway, the one for today, later on, will be, it's called Martian Baseball, How Mighty Casey Almost Saved the Earth. And for the videos that come after this point, you've got a couple more jokes. One's called Don't Touch Me, The Mystery of the Purple Gorilla. And the third one's called The Kid Who Couldn't Stop Saying Strawberries. So that's what you have to look forward to. We'll see how we do here, and we'll get to the hopefully the first one at the end of this video. I'll make it a priority, keeping my priorities straight. All right. This, to me, is the most fun part of the course. So I'm saving the most fun part of the course for the end, but it's also probably one of the most difficult to deal with. They're kind of long problems. You have to do lots of different things as you try to attack these problems. So they take a while, and that's probably what makes it the hardest part of the course. Let's consider an example. This will be our main example for this video. dx dt equals x times y plus, excuse me, I'm going to do a minus 4x, and dy dt equals y minus x squared. Okay, so dx dt is xy minus 4x. dy dt is y minus x squared. This is just a pure system of differential equations. There's nothing about an application here. Probably the main applications that you see in this chapter are going to be to interacting species models, but there are certainly other applications besides these. First thing I want you to note is that it is a nonlinear system. X times y is a nonlinear term. X squared is certainly nonlinear. There are linear parts to it, a negative 4x there and a y there. Those are linear parts to these right-hand sides, but there are nonlinear parts too. Well, we've dealt with nonlinear systems before. Before, you basically just trusted the computer, whether it be Euler's method or HPG system solver or ND solve on Mathematica. Those are lots of different things, lots of different approaches that we've used to try to understand a nonlinear system. And we have used an algebraic approach in terms of trying to find equilibrium points. Let's go back up to the screen here. We need to set both right-hand sides equal to 0. And solve the resulting system of algebraic equations to find equilibrium. The first equation, we can factor out an x to say that x times y minus 4 equals 0. And the second equation is equivalent to saying y equals x squared. Let's see if we can just solve these by thinking about them here, which was what you would have to do pretty much anyway. Certainly this first equation is going to be true when x is 0. And when x is 0, y is forced to be 0 to make the second equation true. That means the origin is an equilibrium point. It seems like the origin is always an equilibrium point, but I will warn you that there certainly are plenty of examples where the origin is not an equilibrium point. But it is one here. Are there any others? Well, certainly y equaling 4 will make the first equation 0 also. And if y is 4, the second equation gives x squared equals 4, which has two solutions. X is plus or minus 2. So we have three equilibrium points. Three equilibria. -2, 4, 0, 0, and +2, 4. I could have written these, I could have combined the first and third as plus or minus 2, 4. Well, I'll write them as three equilibrium points like that. So what do? Probably now we just plot those points and trust the computer, but we are trying to avoid the computer for the most part here in this video until the very end when we can just confirm what we've done. Can we try to draw the phase portrait in the phase plane without a computer? We can, but it takes a bit of work. Here's the first thing I would do, and again I'm trying to think of sections 5.1 and 5.2 kind of all at once here. You will of course read about section 5.1 first before section 5.2 and do homework problems in section 5.1 and before 5.2. I want to think of them as kind of a unit though. Even though in section 5.1 you focused first on trying to understand the nature of the phase plane near the equilibria as your first step, it's not what I want to do as a first step once I've found these equilibria. Instead, I want to do the following. I'm going to draw the phase plane. Go ahead and draw in my equilibria. 0, 0, 2, 4, and I think I'm going to make it so the scale is a little different on the x and y axes, so I don't have to go too far up here. Even though technically, if the scales were the same, the point would be like right about there. I'm going to make it so it's a little easier for me to draw the whole picture. I'm going to put it more in the middle right there of that part of the first quadrant. So I'm going to think of that as the point 2, 4. And then the point -2, 4 will be over here, approximately. So those are my equilibria. Try to draw this a little bit better. It is important to try to draw these things as carefully as you can because the diagram is quickly going to get pretty messy. What I'm going to do now is instead of focusing on what the phase plane looks like near the equilibria points, which is what the focus is in section 5.1, instead I'm going to focus on what are called nullclines. There's an x nullcline and a y nullcline. Here's how you spell nullcline, N-U-L-L-C-L-I-N-E. The x nullcline is going to be a curve or combination of curves in the xy plane where dx dt is 0, where the instantaneous velocity, well maybe I'll say the instantaneous speed along the solution curve as it crosses an x nullcline in the x direction. The instantaneous speed in the x direction is 0 along an x nullcline. Got that? Think of that again. Along an x nullcline, anytime a curve passes through that, at the instant it passes through that, it's going to be vertical. There's going to be no speed in the x direction in either direction. The horizontal component of the velocity vector will be 0. How do you find the x nullcline? You set the right-hand side of the dx dt equation equal to 0. When dx dt is 0, that's going to be the x nullcline, where the instantaneous rate of change in the x direction will be 0. It's going to be when x is 0 and y is 4.
But you don't want to think of those as points. You want to think of those as graphs in the entire plane. The vertical line at x is 0, which is the y-axis, and the horizontal line at y equals 4, which is a horizontal line at y equals 4. So down here I'll label it this way: x equals 0 and y equals 4. Those two lines together form my x nullcline. I'm going to draw it in blue on the axes here, so I'm going to just go over the y-axis in blue. You can't see it real well in blue, I suppose, but that's going to be one of the x nullclines. And the horizontal line at y equals 4 is going to be one of the x nullclines. And I like drawing little hash marks now. In this case, little vertical hash marks, to remind myself that these are x nullclines, that the vector field along these lines is vertical, and solutions will pass through these x nullclines in such a way that they will have a vertical tangent when they cross these. Now, that means it'll cross straight up and down here at the instant it crosses that. But since the y-axis itself is an x nullcline, which is a vertical line, in fact, you're going to get some straight line solutions for this system. You're going to get straight line solutions that start on the y-axis, will stay on the y-axis. Any initial condition on the y-axis will stay there. We're not focusing quite yet whether you go up or down, just that you do go up or down along these two lines. What about the y nullcline? Or maybe I should say nullcline, since we are having more than one curve here. But I'll just label it nullcline. Showing up okay? All right. That's going to be where the instantaneous velocity in the y direction is going to be 0. The y component of the velocity will be 0 when you cross a y nullcline. Going back up to the original system, set the dy dt equal to 0. The right-hand side equal to 0 there, which means the y nullcline is the graph of y equals x squared. It's going to be a parabola. Y equals x squared, and if you think about it for a minute, you'll realize it goes through all three of these equilibrium points. Like this. In fact, the equilibrium points are going to occur where red and blue cross. Anytime an x nullcline crosses a y nullcline, and vice versa, that's where you're going to have equilibrium points. Those are the only places that you can have equilibrium points, is when the y nullcline crosses the x nullcline. Now, the x nullcline crosses itself. You don't have an equilibrium point where an x nullcline crosses itself. At this point right there, 0, 4, that's not an equilibrium point. An x nullcline has to cross a y nullcline to get equilibrium points, because that's going to be where both equations are 0, both right-hand sides are 0. There's no motion in either the x or y direction. You're staying at an equilibrium point. A good next step, now this is all so far really section 5.2 material, is to figure out, based on the regions these nullclines break the plane up into, where is the vector field pointing up and to the right? I guess that would be northeast. Up and to the left, that would be northwest. Down and to the right, that would be southeast. And down and to the left for you here, that would be southwest. Where is that going to happen? Let's think about the y nullcline first. And again, I'll label it down here with y equals x squared. The y nullcline is where dy dt is 0. Where is dy dt positive and where is it negative? You've got to go back up to the original equation and think about it here. The original equation has a right-hand side of y minus x squared. That's going to be positive when y is bigger than x squared, when you are above this parabola. all solutions are going to be going upward, either northeast or northwest, when you're above that parabola. So I can draw in some upward pointing arrows here, 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 and here. So far I haven't drawn any solution curves except for the equilibrium points. None of these things are solution curves. Oh, I guess I forgot to make my horizontal hash marks along the y-nullcline. Make them small horizontal hash marks. And when y is less than x squared, when I'm below that parabola, that's when my solutions are going to be going down. So I'll put downward pointing arrows in these other regions. I guess it looks like I'm kind of artificially making the x-axis be a separator here. It's not really. It's not an x or a y nullcline. So in reality, I could have just drawn one big down arrow in this entire region over here, and one big down arrow in this entire region over here. What about the x nullclines? Where is our solutions moving to the right and where are they moving to the left? That's a bit trickier. Go up here. You got to think about the sign of this thing based on what region you're in. Think about how the x nullcline looks down here. It looks like a cross or a plus. When you're up here, it's going to be one thing. When you're over here, it's another. Down here, it's another. And down here, it's another. There's 4 cases to think about. Think first about the case when we're up here, when x is positive and y is bigger than 4. Both of these factors will be positive. dx dt will be positive. So you'll be moving to the right over here. I guess I should put a downward arrow over here too, and a rightward arrow over here. When you're over here, in this region, x is negative and y is bigger than 4, so negative times positive gives you negative. dx dt is negative, so your motion of solution curves is to the left. When we're down here, x is negative and y is less than 4. You've got a negative times a negative up here at the top. So that's a positive. You're going to be moving to the right. dx dt will be positive. And finally, when you're over here, x is positive and y is less than 4. You'll get a positive times a negative. Overall, giving you negative motion to the left. Okay, so we've gotten a lot of information without figuring out what the solutions look like near the equilibria yet. In fact, you can kind of draw the phase portrait just from this information. But it is also good to use the techniques from section 5.1, which is what I want to focus on now, to look at what's happening near the equilibrium points. Do you remember in your calculus classes that you may have had problems like this? Approximate square root of 9.1 without a calculator. And you wondered what was the point. We have calculators, so why would we want to do such a thing without a calculator? And maybe your teacher said something like, well, how do you think calculators are programmed? And don't you want to know that? And, what if you didn't have a calculator and this is the way they used to have to do things? The technique for this was based on linearization, based on using tangent line approximations, in this case to the function square root of x, near x equals 9, to approximate the answer. The answer is just going to be a little bit bigger than 3. If we could use a tangent line approximation to the graph of square root of x, near x equals 3, we could probably, the tangent line is going to approximate the curve, and so we could use that tangent line to approximate the graph of the function, and therefore the value of the function when x is close to 9. And you probably thought, oh, this is so phony. Why would we do this? Well, now you're going to see the full fruits of linearization. Linearization, in this kind of sense, but in a more general setting, is going to take on a lot more significance. what we're going to do is we're going to go back to our original equations. dx dt equals xy minus 4x, and dy dt equals y minus x squared. And we're going to linearize the right-hand side. What does that mean? Well, it's easiest to understand if you linearize near the origin, especially if the origin, like it is for us in this example, happens to be an equilibrium point. How you linearize near the origin, which is an equilibrium point here, is you just get rid of all the nonlinear terms. When x and y are both close to 0, the linear terms, the negative 4x and the y, are what is going to dominate. Everything is going to be small on the right-hand sides when x and y are close to 0, but the nonlinear terms are going to be relatively much smaller, and the relative scale of the sizes of these things, the linear and the nonlinear term, gets more and more extreme the closer and closer you get to the origin. Just to make up some numerical examples in my head, if x were, say, 10 to the negative 5 and y were 10 to the negative 5, then 4x and y are on the order of 10 to the negative 5, whereas x times y and x squared are on the order of 10 to the negative 10. Both small numbers, but 10 to the negative 5 is 10 to the 5th times as big as 10 to the negative 10. 100,000 times bigger. So on a relative scale, it is a significant scale difference. Essentially, we're going to use some approximate equalities to say that this is approximately negative 4x and this is approximately y when x and y are both close to 0. Technically speaking, what we are doing, or what we're going to do, is we're going to create an associated linearized system. Linearization of this system at or near the point 0, 0 is a different system. I'm going to write equal signs now. This is a different system than our original nonlinear system. This is a t here. dx dt and dy dt. dx dt equals negative 4x, dy dt equals y. All I've done there is I've taken the right-hand sides up here and placed them down here, and I'm not using approximate equalities anymore. I'm writing actual equalities. This is a different system than this, even when x and y are close to 0, but they're going to be real close to each other. In fact, their vector fields may be basically indistinguishable from each other when you're looking real close to the origin. So, solutions of the linear system should be very close to solutions of the nonlinear system when you start out close to the origin. As you go further away from the origin, they certainly can get very different from each other. But close to the origin, they should be the same. And we know from Chapter 3 how to deal with linear systems. In fact, it'd be convenient in general to put these things in matrix form. The corresponding matrix vector form of this system is like this. I guess I could have just written that as capital Y. And I've got a coefficient matrix A, and I can use the trace determinant plane to help me quickly figure out the nature of the eigenvalues. And I could also solve for the eigenvectors. In fact, this is a diagonal matrix, so the eigenvalues are the numbers on the diagonal. The eigenvalues are negative 4 and 1, 1 negative, 1 positive. Think that means the origin is a saddle point for this linear system. It also means it'll end up being a saddle point for this nonlinear system. Since it's a diagonal matrix, the eigenvectors actually end up being very simple too. For negative 4, since that's in the top left corner, it turns out the corresponding eigenvector will be 1, 0. And for 1, the one in the bottom right corner, it turns out the corresponding eigenvector will be 0, 1. The eigenspaces here are along the x and y axes when you've got a diagonal matrix like this. So in fact, the phase portrait of the linearized system has the origin as its only equilibrium point. -4, that's the negative eigenvalue with eigenvector 1, 0. That tells you you've got a straight line solutions going in toward the origin along the x-axis. +1, that's a positive eigenvalue with eigenvectors along the y-axis, so you're going away along there. This is sort of your prototypical saddle point. You could probably draw this a little bit more accurately, realizing that -4 is much further away from 0 than 1 is. Probably what really happens is these go in toward the y-axis faster than they move up because of that. But I won't worry about that. What does this tell us? Going back now to the original picture, in a small neighborhood of the origin, the picture is going to look exactly the same. You'll be going, let's see, yes, up and down, away from the origin along the y-axis, toward the origin along the x-axis, though you got to be careful here. It really is actually not quite exactly along the x-axis here, but it's going to be very close, practically indistinguishable as you get toward the origin. In reality here, if you think about the directions of these arrows over here, it's got to be doing something like that, because you're in this region where you're moving down and to the left, southwest. So it's got to be going down and to the left before it kind of approaches the origin along the x-axis here. A similar symmetric kind of thing has to happen over here. The x-axis is not a straight line solution for the nonlinear system. When y is 0, dy dt is not 0. Okay, so in fact it's going to be negative when y is 0, as long as you're not at the origin. So it does have to look like this. But as far as a local picture in the neighborhood of the origin here, if I just sort of draw a dashed little circle around the origin here, basically the picture would be indistinguishable from this other picture. If you zoom in near the origin of this nonlinear system, the closer you get to the origin, the more it'll look like this. So you can try to be a little bit more careful here. You can also draw in some solutions that go like that. And if you kind of work backwards, they have to cross this y nullcline horizontally. And then they're in this region where as t increases, they move to the southwest. So as they move backwards in time, they have to go to the northeast. You're going to get something like this. I know it's getting hard to see this kind of, but this is the kind of thing that's going to happen here. Ignore this black mark here. See if I can erase that. You can see why this is a process that can take a while. Okay? You would also have some solution curves down here. They're going to go close to the origin, but not quite, and they have to act like the saddle point on the other slide and go down this way. In fact, they can't cross the y-axis by the uniqueness theorem. They're going to approach the y-axis as t goes to infinity, and same kind of thing over here. They get close to the origin, but then go down like this. So that's nice. We've got a good picture of what's happening near the origin. What about near these other equilibrium points? Well, I'm running low on time for the video. What I was hoping to do was show you how to transform the equations to new variables that allow you to get rid of nonlinear terms in terms of those new variables. See, you don't want to get rid of these nonlinear terms like this when you're near the other equilibrium points because they're not small anymore. In fact, none of these things are small necessarily when you are near those other two equilibrium points. Let me just show you the really neat trick as quickly as I can that allows you to find what's going on near those other equilibrium points. This is the main trick you're going to be using for section 5.1. You'll learn about throwing away nonlinear terms, but you'll also learn about finding something called the Jacobian matrix. J for Jacobian matrix. It ends up being a matrix that's found this way. Its entries are partial derivatives. This is kind of weird. I know. Little f represents the right-hand side of the dx/dt equation. Little g represents the right-hand side of the dy dt equation. And in fact, if you think of the right-hand side as a vector field, little f is the first component of the vector field, and little g is the second component. Take the derivative of f with respect to x, put it there. With respect to y, put it there. Then go to g, take its partial with respect to x, put it there. Its partial with respect to y, and put it here. For this problem, I'll do this quickly. F was xy minus 4x. G was y minus x squared. The derivative of this with respect to x is going to be y minus 4. Think about that. Treat the y as a constant. Differentiate with respect to x, you'll get y minus 4. The derivative of that with respect to y is just going to be x. In the second component, the derivative with respect to x is negative 2x, and the derivative with respect to y is 1. What you want to do with this matrix is plug in those other two equilibrium points. And you could also do this with 0, 0. Evaluate this Jacobian matrix at the equilibrium points. If we're at 2, 4, then y is 4. So this upper left entry becomes 0. Just want to double check what I'm doing here. Hopefully I'm not making a mistake. X is 2, so plug in a 2 there. Negative 2 times 2 is negative 4. This is a 1. The trace of this matrix is 1. Determinant is going to be 0 minus negative 8 or plus 8. In the trace determinant plane, it's going to be up here a ways. You're going to be above the repeated root parabola. Ultimately, what this is going to tell you is for the linearized system, the linearized system of this is, by the way, for this equilibrium point, I can get from reading off this coefficient matrix. That's a positive 2. dx dt is positive 2y, and dy dt equals negative 4x plus y. That linearized system by this trace determinant plane is going to have a spiral source at the origin. You can think about that, of the origin for this linearized system. This is not the original system. Ultimately, what that's going to mean is that the 0.24 for the original nonlinear system is going to be a spiral source, whose graphs are going to look a lot like the graphs of the linearized system near its origin. So we're going to get a spiral source here, and you can figure out what direction the spiraling is by looking at these arrows. It's got to be clockwise. And if you kind of follow the arrows and the hash marks, you begin to see that it's got a spiral about like this. I'm going to continue with this example in the next video. We'll try to finish off what this phase portrait looks like. To give you a little hint, I think we get another spiral source over here. And one other interesting thing that happens is there's got to be one of these spirals ultimately that heads down toward this equilibrium point. And such a solution curve has a special name that you'll read about in section 5.1. It's called a separatrix. There's got to be one solution curve. Not all the solution curves here that are spiraling outward, but one of them, it should make sense, has to sort of come down here in such a way that it meets up with this one here. If I follow that one backward in time, I should spiral backwards toward this equilibrium point. And those will be important too, those separatrices. But now the really important thing, this joke. The joke for today is Martian baseball, how Mighty Casey almost saved the Earth. And I guess I have to, this is supposed to be a long and lame joke. I have to kind of shorten it a little bit because otherwise this video is going to be too long. So this is the real quick version, okay? Martians have taken over the Earth. And They're tyrannizing the population, but they give Earth a second chance. They say, we'll leave you guys alone if you just beat us in a game of Martian baseball. There's a catch. Martian baseball is something that Martians are really good at and Earthlings are not, because when they hit the ball, it's allowed to go out of the stadium, and they have strong enough hitters to hit it out of the stadium, and they're allowed to run around the bases as many times as they want and keep scoring runs over and over and over again. The Earthlings did have a hope in Mighty Casey that Mighty Casey could hit balls out of the stadium and continue running around the bases, but Mighty Casey didn't show up for the game day. And the Martians were just wasting the Earthlings. By the 9th inning, the score was 1,000-0. Things were looking pretty down, but then Mighty Casey showed up. The Martians were a little concerned, but they weren't too worried. Mighty Casey was at bat. He hit it out of the stadium. He starts running around the bases, over and over again. The Martian outfielder runs out of the stadium, runs after the ball, and this ball is specially marked, by the way, so they have to use the same ball that was hit. It's rolling down the street. The Martian runs after it, can't quite catch it as it falls onto a helicopter that's taking off. However, that might happen. Helicopter takes off, and the Martian's really upset, and he gets in his own helicopter and chases after that helicopter. Helicopter lands, the ball bounces out, the ball bounces into a jet airplane. The jet airplane takes off. The Martian jumps out of his helicopter, jumps into another jet airplane, starts following after the ball. Meanwhile, Casey's continuing to go around and around the bases. The score is now 1,000-100. Chases after it in his jet airplane, shoots down the other jet airplane. The ball flies out, lands in the ocean, well, not quite in the ocean, onto an ocean liner that's moving across the ocean. The Martian comes after the ocean liner, can't really shoot the ocean liner out of the water, so he lands, tries to find the ball on the deck. By the time he almost finds it, they're across the ocean. The ball rolls off as they make port and starts rolling down the street. The Martian runs after it. Our motorcyclist picks it up. The Martian gets a motorcycle, chases after the ball, finally jumps the guy on the motorcycle and grabs the ball. Okay, by this time it's about 1,000-500 now. Casey is getting pretty tired, but he keeps going. The Martian quickly comes back to America as quickly as possible. Has to get on an ocean liner coming back across, finally getting in a car or something and traveling around the country or part of the way across the country to get back to the stadium. It's 1,998. Casey's got to go around 2 more times to tie it, 3 more times to win. And the Martian's coming into the stadium. The crowd is going wild. Will Earth be saved? It's 1,999. Then it's 1,000-1,000. It's tied up. The Martian throws it toward home as Casey's coming around third base. There's a big cloud of dust as Casey slides. At about the same time the ball comes in, the catcher grabs it, puts the tag on Casey. Everybody's quiet. They all look up at the ump. Foul ball! And that's the first long and lame joke.